Hi everybody, welcome. It's Thursday, September 3rd. It's 5 p.m. and it's a very exciting time. We're gonna, I guess I can just let this kind of crank go on in the background here. But we're gonna talk a little bit about telescopes again. It's Ask an Astronomer. I might just do this, let's really, oh gosh, let's do this. I hope everyone's having a nice day. Hi Vitalis. I'm doing great. I'm wearing my Eugene Science Center shirt, and I have a little bit of a headache, which isn't great, but whatever. And I'm excited to talk a little bit more telescopes. I decided to do something today that is a little fun. In the last couple of weeks, I've been switching to something that's kind of difficult to do in Space Engine proper. But I thought maybe it would be fun to, instead of just like bringing up images and going from image to image, put them together like a lecture. So actually I'm using slides from when I gave a lecture at Dartmouth College for a class on the solar system. I'm using my lecture notes, my slides for telescopes. So there might be some stuff in there that's more lecture-y, but whatever, this is kind of how this is. And what's cool is if you have questions, you can ask me. So what we're going to do today is we're going to talk a little bit more telescopes. I'm going to talk about the telescope that I work on at the end of the day, which would be kind of fun. And again, at any point, just ask some questions, and hopefully I can answer them. So I want to start by talking a little bit about what we did last time. So last time we talked a little about light, and we talked about how light works. And so here's essentially how light is a thing that we talked about a little bit last time called refraction, which is this idea that when light goes from one surface, like one medium to another, it bends, it changes. And the way you can think about that is like we've got, this marching band that goes into sand where it's a little slower from when they're in the asphalt, then their line is going to essentially change directions, because they're trying to go the same direction, but they can't go as, the same direction in that medium, or they can't go the same speed in that medium, so they turn, right? And so this angling in the different medium is exactly what's going on when you angle the light that goes into glass, for instance. And we can use that along with reflection, which we'll talk about in a second, to essentially focus light. So here's how a lens works. You can see the light goes in here, and when it enters the medium, in all cases, depending on the angle with which it enters, it bends. And so the light bends a little bit, and when you get all these bending, like and you curve this glass correctly, it can focus on a focal point here. So this is the premise of how magnifying lenses work and how lenses just work in general. Well, lenses in your glasses and all sorts of stuff. Is essentially they take light and they bend it so that it focuses in a different place than if it were just going straight forward. And so what that means is with a magnifying lens, essentially when you look at a magnifying lens, like the light that comes into the lens from this ant here, when it goes through the lens, when we see it, we see light and we think it travels in straight lines. It's hard for us to see light and think it curves because that's just the way that our brains work, is they think light travels in straight lines. So the light from the head of this ant or whatever, when it goes up into this part, as it gets bent in here, it looks to us like a virtual image of this head and a virtual image of the body, right? Like you get this big, long, stretched out thing because the light is bent. From a small region, it's bent over a larger region, which makes it look like it's being magnified. And this is essentially the way that magnifying lenses work. And what's great is that you can use this in conjunction with another lens to, an eyepiece lens and an objective lens. So the objective lens essentially does the focusing, and the eyepiece lens essentially unfocuses it back for our eye to take light from a distant object and magnify it towards our eyes, right? And so a telescope then makes things that are distant and very small appear larger to our eyes. So it's essentially kind of what this is doing, but we don't have to have your eye at the exact focal point there. You can actually use this eyepiece lens to defocus and then use your eye as well. So this right here is called a refracting telescope, and we talked about this last week, that they don't make a lot of a couple weeks ago, they don't make a lot of refracting telescopes because there's some problems, which we'll get to in a second. But this is the kind of basic early ideas for a telescope in the 1600s were these types of telescopes were developed as a way to look at incredibly distant objects. And the important parts of a telescope are, and I've written here, but essentially the important thing is the diameter. with telescopes, the bigger the better. So the bigger a telescope is, the larger its diameter around of its lens or of its mirror, of the light gathering element, we call it a mirror or the lens. That's the better that the telescope is. So here you've got two images of the Andromeda Galaxy, which I talked about on Sunday, by the way. If you were watching my other video series on how to stargaze, you saw that you can actually see Andromeda with your naked eye. It doesn't look as good as it does in these images, but in the top image here, you see it. These are both taken at the same exposure time and the same magnification, meaning that you've actually magnified the thing. They're the same size in the sky. You can see these other two galaxies down here on either side are essentially like, it's not like you're zoomed in on one versus the other. They're the same zoom level or magnification. But with the lower one, you actually see a lot more detail, right? You see, first off, it's like, you can understand what's going on in the arms and stuff. But secondly, stuff that's over on the edges here, you can't see it, but you can in this. And that's because while it's the same exposure time, and it opened the shutter and took this image with the same length of time in both images, the bottom one had a larger telescope, which means for the same amount of time, you get more light. And the larger diameter means you can resolve, because you have a larger diameter mirror to focus, you can resolve better details, right? And so with a larger diameter lens, you get more photons per second, more light per second hitting off the mirror, and you get better detail of what you see. So with telescopes, bigger is better. Okay, and that's why we'll be talking today at the end about some telescopes. And generally when you're gathering light like this, you want a bigger telescope, but it's kind of tough to make bigger telescopes. And so here are the things we talked about a couple weeks ago about why you wouldn't want to use lenses, which is that lenses have to be free from defects to get the light to pass through. So you have to have a glass that's like perfectly defect free, and that's really expensive. It doesn't allow all wavelengths of light to pass through. So a lens, you can't get like infrared or ultraviolet radiation can't pass through. So if you wanted to make an infrared telescope with lenses, you couldn't, because the infrared light would just get absorbed or bounce off of the lens, which is bad. That means that only optical light can make it through, and some other wavelengths of light, radio waves as well, can make it through the lens, but radio waves don't get refracted by the light. So, but that's bad. And then finally, they suffer from chromatic aberration, which we did discuss, where you see here in the bottom image, you see all of these, the same image, but where the light is kind of blurred by color because it's passing through a lens, right? Which is bad. And with a large lens, you have to support it around the edges only, right? And so if that's a small area that's being held on, and it could, that's not great if it's a very, very heavy lens. And then on top of that, glass is not a great solid. It kind of sags and over time, changes shape. And that's bad, because if the lens changes its shape, it's not as good as the lens anymore. So what we did was we came up with another way of looking for making telescopes, and that was by using mirrors. So this is the Newtonian refractor. This is Isaac Newton's own little telescope here, which is 3 centimeter diameter, had a magnification of 402. And this essentially uses something where, as you can see here, light comes in, bounces off a mirror, bounces off a secondary mirror, and goes through the eyepiece here. So instead of a lens doing this focusing, a mirror does. But now notice that the focusing would be way over here, but you'd have to put this little secondary flat mirror in the way. And you're saying, well, doesn't that block the light? Can't you see the mirror? Well, the thing is that this only blocks some of the light. A lot of light still gets through, and that ends up not mattering a huge amount. It does when it comes to diffraction, but I don't want to really get into that right now. But what's cool is that with this mirror, you only have to support it on one side, and you can polish that one side perfectly. It doesn't have to be, you don't care what the mirror is made out of, except that the surface of the mirror is really polished, which is very cool. So here's a telescope I've used so often. I took this photograph. This is a telescope that's just south of where I live on Kitt Peak, and it's a 2.4 meter mirror. So the mirror is this, I've kind of drawn it in white here, and it's a professional telescope. It's kind of an older professional telescope, but it's still being used. I've used it for science that I've published, and you put it in this dome here, and I'll talk about that in a second. But the light will come in the telescope, bounce off the primary mirror, bounce off a secondary mirror, which is why I put in white here, and then into the camera, which is down at the bottom here. Okay, and the other parts of this telescope, which I didn't talk about. Oh, by the way, this is called a Cassegrain focus reflecting telescope, which who cares? I mean, if you want to look up these sorts of things, there's different types. This is not a Cassegrain focus. It's a different. The focus is up here on the side as opposed to going through the bottom. But this one, when it goes through the bottom, that's Cassegrain focus. And a lot of telescopes are like that because you can dump all the instruments on the backside of the telescope and the mirror there. And then, but there are many where it'll bounce off, it'll point in one way, and then they just put the instruments around in the edge, you know, when it's really large. In a telescope like this, like it's put in a dome. We'll talk about that in a little bit later. And the dome has this slit right here. The slit opens up and allows you to look through the telescope straight there. So the telescope generally will point always where the dome slit is. So if the telescope moves, which we call slewing, the term for moving a telescope is slewing. If you slew the telescope to a different part of the sky, the whole dome will rotate. So the slit will point to where the telescope is, right? Because otherwise you couldn't see the dome. These arms, this is the mount of the telescope. And this mount is mounted in such a way that you want it really well balanced. You want to put counterweights on it so that really you don't have to have very, very powerful motors to move it. You can have really nice motors that can have very fine motion. Because it's counterbalanced so well, you can just move it a very tiny bit and it'll move without having to like really give it a bunch of power to move it. And that is like vital because what a telescope mount has to do is move the telescope over the course of the night. Because the Earth rotates around and moves, the sky essentially moves over the course of the night, you have to point to an object and then track it. So the word we call track it as the Earth moves, and that requires little fine motors. If you've ever, here we can watch. Well, let me show you what happens if we don't do that. So let's turn off this thing here, and let's go back to Space Engine. I'm going to set it to now and normal time speed, and we're going to go to the Earth. So, hello Earth. Where's the Earth? I'm very confused. Oh, that's why, because I'm focused on the sun. There's the Earth. Okay. So if we go to the Earth, I don't know why I do that sometimes. There we go. If we land, okay, here we are. Let's look for something we care about, like, you know, we zoom in, so next to the moon here. So I'm going to point up here. And now time should be going on. And notice, if I put my mouse over one of these, how things are moving, right? Things are slowly crawling downward. It's a little hard to see, but, you know, if I increase the time speed a little bit, you can see a little bit better, right? And so through a telescope, like, you know, things would move. This is a bummer. Because if you want to, like, take a long exposure through a telescope where you're looking at something over a long period of time and really getting out the faintness of it, you don't want it to move because then it'll smear across your image. That's bad, right? And you may have seen images of what we call star trails. Like if I look up star trails. So let's bring up a web browser. Do I have a web browser? Internet? Bye-bye. Aha, there we go. So if I look up images of star trails here, you can see this image here, or this image right here. This is what happens if you just point your telescope at the north, open the shutter for a long period of time. How do I know that? Well, let's show you. Let's do the same thing, right? So if I look down here, let's see if we can figure out which way north is. I don't know where I am on the planet. What do we have down here? Is this? It's Venus. This must be in the west. The sun should be rising. No, wait. Yes. So this is the west. The sun is rising. So this is the north over here. And so if we point north, we're in the southern hemisphere. That's why. If we point south, then let's look south in that reason. If we turn on speed, okay, the sun's going to cross over the whole sky. Actually, here, let's fly off into space. So you see how the stars are kind of motoring around like this? And if we make it go even faster, you can see that they make this, like, you know, essentially down over in this direction. That's the Earth rotating. We're kind of sitting on the Earth as the Earth rotates around. And that, okay, it's a little hard to take. And that is essentially what's going on in our star trail images. It's just you open the shutter for long enough that you can see it. And the reason that this is done so well is because they probably have added a couple bits, but also because they're looking in the north and they've got sunrise to sunset, which is where you're starting to see a little bit of stuff near the horizon on either side. All right. Motion blur. Exactly. Motion blur is bad in astronomy, essentially. Because motion blur is what you don't want. And so what you really want is you want some sort of motor that can track an object, and so like you could imagine that if you like you're taking a cell phone video and you tracked a car that drove by really fast, then the car would be fixed, everything else would be blurry around it. And so the thing is you can track the sky's motion to reduce that motion blur. Thank you, Metalis. And to do that you use a motor. And so in this case, the motor on the telescope here is inside of this mount here. And then on the bottom is the cameras. And so for this telescope, I think they only have one camera on at a time. And I think that this may have been when Osmos was on, which is a spectrograph that I used quite a bit when I was at Dartmouth. But the camera is something you could swap on there. Some telescopes you could put multiple cameras on and then change the light path to it. Like I'll talk about a telescope later. With many cameras here on the ground, you put one camera on for a period of time and then you swap it out over the course of the day. This camera also, this blue thing at the very bottom, I don't know if you can see that very well, that is a thing that keeps the camera itself, like the detector, the chip, really cold, because you want to make sure that you don't get spurious light from the heat of the camera itself. And that's because you've got to be very, very careful about light sources. You want to make sure that your telescope is very, very dark in this room and there's no extra sources of light, because you don't want that to interfere with the light you care about. But we'll get to that later. This is a pair of telescopes in Hawaii that I've also used. These are the telescopes on Mauna Kea, and they're two twin 10-meter telescopes, and they're on a mountain top. Actually, they're on a volcano top, a very sacred site for the native Hawaiian people. And if you look down here, this is a zoom in to show one of the telescopes. You can see here that, like a telescope we'll talk about later, it's mostly composed of these hexagonal mirror segments, but very similarly to the one I was showing you here, where you're looking at the primary, and the secondary would be what it bounces off of. The secondary is over here. You can see the secondary up in the top here. So the primary, the light comes in here, bounces off here, through here to where the instruments are. So this is a 2.4 meter mirror. This is a 10 meter mirror, which is one of the biggest in the world. We'll talk about that in a second. This is Gemini South, which is just a little bit like in Chile, where the Gemini Planet Imager is installed, this instrument that looks for planets. And here you can see some of the people with the telescope itself. So look at how tiny they are compared with how big the mirror is, right? This giant mirror and Gemini Planet Imager and Gemini South. I've been to Gemini North, which is on another one. It's on another ridge on this image, like so it'd be over on the right. But this is Gemini South, and you can see, this is the same thing as I was talking about. There's the dome here, and then these are called louvers. And at night, you want to open those louvers to let a little bit of airflow through, but you want to keep it generally pretty enclosed from any winds or anything. So with a telescope, you want to essentially remove any possible weirdness from the atmosphere, because, and we'll talk about it later, because the atmosphere does a pretty nice job of blurring your images, which is bad. And so that's why you use these telescope domes with these slits on them. But you can see telescopes come in quite a bunch of shapes and sizes, because the bigger the telescope is, the more light gathering power it has, which means the better detail and the more light it can get per second. So what you want is a really big telescope so that you don't have to worry, so that it's easier to get a bunch of light in the same amount of time. Like imagine if you had like an hour only to observe, you want to make sure you have the biggest telescope that you can, unless it's overkill for the project you're working on. For the stuff that I do, which tends to be pretty far away galaxies that are very faint, where you want as much detail as possible, I like having larger telescopes. Here is a really fantastic chart showing the sizes of either proposed telescopes and existing telescopes. Okay, and so you can see, I talked about last week the Yerkes Observatory in Wisconsin, which is the largest refracting telescope, and it was built in 1893 and is 40 inches across, right? There's a great Paris Exhibition telescope, which has a lens here, But these are the largest largest lenses that we built for telescopes. After that, we started building telescopes with mirrors. Earthquakes are an issue for telescopes. especially in California, where many of the big ones like Mount Wilson Observatory, you can see the Hooker telescope here, Mount Palomar, and like these two are like in areas where earthquakes can happen, and generally earthquakes happen on a time scale. It's nice to see you, KJ. Happen on a time scale where they shake things and then they stop. And you generally, if that happens, you get to safety and you just throw that data out. It's not like a thing where an earthquake happens over the course of, months. And telescopes are built not just where they're anchored to the ground, but they're anchored so that if there is a lot of earthquake activity, they're a little bit removed from that. Seismic activity, cars driving outside that could jostle it. Because you're right, you want very limited jostling. So the telescopes that I also showed you, the Keck telescopes here and Gemini North and Gemini South here. I guess I showed you Gemini South and the Keck. So you can see how big these telescopes are compared with, the Yerkes Observatory, right? That largest refracting telescope. But you can see that we've built other the Grand Telescopio Canarias in the Canary Islands. There's the Hobby Eberly and the South African Large Telescope, which were built in a very similar fashion, but one's in the Southern Hemisphere and one's in Texas. I've used this telescope quite a bit when I was at Dartmouth, and it is an interesting design in that most telescopes sitting in here, you can see all of this is motors to make sure that the telescope can slew to different spots in the sky. They can turn this way and then go up and down, right? So generally they'll go and then or down to where they need to go, right? And then they start tracking over the course of the night. But with these telescopes, they're actually fixed, and they can and then there's another mirror that can essentially track that. Am I buffering? Am I dropping frames right now? Uh-oh. I'm in a period of okay, I'm good now? Oh, the internet just died. My wife's on an important Zoom call in the other room, so sorry about that. But you can hear me now. We're all good? We're good? All right. So anyway, these planned missions, the 30-meter telescope, the European Extreme Large Telescope, they're the next generation of telescopes on the ground. But for right now, the largest optical telescopes, the Keck telescope here, the Gemini North and South, these are the biggest ones. In space, we have the Hubble Space Telescope, which is one of the largest, and then the next one is the James Webb Space Telescope that says planned 2018, and turns out probably going to be 2021 next October. So it's not ideal how long it has taken. When I got the job, when I put this on, it was supposed to be 2018. This is a little out of date. But these telescopes will be in the next 5 to 10 years, and they are going to be incredible. Like I can show you, like the giant Magellan telescope, GMT. So I'll tell you in just a second, Metalis, how far we can see in space, because that's like a complicated question. So the giant Magellan telescope will essentially look like this. You can see this, enormous, like here's a YouTube video showing, I'm not going to make it any noise, but like showing what the site looks like right now, because it's not super duper far along. We've built many of the mirrors, but eventually it'll look like this in the same site down in Chile. You have this beautiful giant set of mirrors that all work together to look up at the sky. It's pretty cool, right? So let's turn that back off. And that one is this right here down at the bottom. So my question down here still stands. Isn't the Hubble Space Telescope this incredible? It's the farthest. How is it that we've seen the farthest when these giant bigger telescopes? Can't they see more light? Well, there's a thing. So with telescopes, no, it's okay. You can ask questions and I'll answer them, but I'll also point you. There's other streams that are pretty good. You just can't ask questions live. So with my stream is now healthy again. So with telescopes, you want to understand resolution here. And here's a complicated equation that talks about resolution, but mostly think about it like this. Imagine you're driving down the road and you know, like you're driving down the road and you see a car coming at you, and you're like, huh, is that a car or a motorcycle? Because for a long time it's just like one blob of light. It takes a little while for your eye to be able to resolve that it's two headlights as opposed to one, right? So down here you can see two light sources that when they get close enough together look like one light source, right? And this right here, this is the ability for our eye to resolve close by sources of light. They look like one blob, they look like two blobs. And so, like, as light moves through a telescope, as it bounces off of a mirror, it's also diffracted, which means that what should be like a sharp point source of light gets blurred into these little blobby lights with rings, like you drop something into a pond, right? And so it turns out that diffraction is dependent on the wavelength of light you're looking at and the diameter of your telescope, meaning a bigger diameter, bigger D, the smaller you can resolve, right? So if our eyes were bigger, if we had larger like eyes, like an owl's or whatever, just like enormous eyes, cartoon owl, then we'd be able to resolve better because at the same wavelengths that we can see, the D would be bigger, which means that the resolution would be much smaller. And so here is another thing. It turns out that there's other stuff going on than just like, so then what that would indicate is that, oh, if you have a bigger telescope like Keck, you should be able to resolve better than with James or with Hubble, right? Hubble's a smaller mirror, but James, compared with Keck should resolve. Or Subaru, which is a telescope. Is Subaru on here? Why is Subaru not on here? Magellan, VLT. Subaru should be on here. I'm surprised. Oh, yeah, Subaru's right here. So Subaru telescope and Hubble. I'm going to show you two images from Subaru and from Hubble right now, okay? So Subaru's a bigger mirror. Here's an image of an object. You can zoom in right down here, and here's the same one with Hubble. So what's going on? Why does Hubble see so much more detail, right? Like, you know, it's still pretty bright. They're still about the same brightness. You know, maybe some of these things, but like everything's much more blurry, right? 8-meter mirror. 2.4 meter mirror. 8 meters, like 24, 25, 26 feet. Enormous. But what's going on with it? What else is the difference between the two? Well, where's Hubble located? Subaru is located on the same mountain, on this same mountain here. It's just on another ridge in Mauna Kea, so this volcano. And it's got a mirror that looks a lot like the Gemini mirror here, right? Hubble's located in space. So here's the thing. Our atmosphere is really, really good at letting us breathe. Thank God for our atmosphere and for breathing oxygen. That's dope. Gotta love oxygen. However, what it does also do is that light blurs objects from space, meaning that as the light comes in through the atmosphere, it bounces off atmosphere particles, and that light then blurs out. So what you would expect to be this perfect little circle of light coming from an object through a telescope, so it's a little bit blurred out into this little with the rings, it gets actually blurred a lot more, and you get these little pockets of turbulence and everything becomes a fuzzy blob. You know this. You've always known this because you've sung a song about this. That song goes, "Twinkle, twinkle, little star." Twinkling, the twinkling of light, is because of the atmosphere. When you sit out at night and you look at stars and they twinkle and they're so beautiful, changing their brightness and getting brighter and dimmer, that's the atmosphere, meaning that more light and a little less light is getting to your eye as the rest of it is kind of scattered around. Or it's more focused and less focused, which means it looks brighter and then dimmer and then brighter and then dimmer. It's because the atmosphere. And so if it's a really windy night up in the upper atmosphere, it's going to be worse turbulence, okay? And so we call this atmospheric seeing, or seeing for short. And so astronomers, when they want to talk about how good their astronomy night of observing was, they'll go, "Oh man, what was your seeing? What was your seeing? What was your seeing?" And what you want is you want a low number, because the number indicates how blurred out things are, and you want a real low number. Oh, we had like a 0.5 arc second, 0.4 arc second seeing. We had a perfect night of like 0.2 arc second seeing. Oh, so good. Or an arc second is defined as 1/60th of 1/60th of a degree. So 1/360th of a circle is a degree, and 1/60th is an arc minute, and then 1/60th of that is an arc second. So very tiny little angle on the sky, and a 0.2 arc seconds is like 2/10 of that. So really 0.5 or below is really great seeing. And the thing is we can actually combat seeing. We can overcome bad seeing in certain sites. So this is the Keck telescopes again, and it looks like they're like shooting a laser into space, because they are. They're shooting a laser at the atmosphere. And the atmosphere is producing a fake star. And they can look at that fake star and say, that fake star should be, like it's hitting sodium in the atmosphere and causing it to glow. And they're saying that atmosphere, it's glowing, that little dot, that fake star, should be a perfect dot like this. Instead, it looks like this. How can we reverse this to look like this? And so they use something called adaptive optics, okay? And this is the complicated thing. I'll talk about that in a second, Vitalis. The light comes in, it's distorted from the atmosphere, and then there's a little mirror that learns to vibrate to take the light and go back to a control system, a computer that says, if I vibrate this mirror, can I collect the light? Can I reverse what the atmosphere has done to blur the light, unblur the light with a mirror? And when it does that, it takes light that is very blurry and makes it much more, and the problem is that this is a PDF. I can look at this, and we can bring up this and go like this and go. All right, so let's find the video, because you got to find the really good video. The adaptive optics before and after. Here we go. So you can see here, watch as the adaptive optics is turned on and all these blurry blobs become stars. Adaptive optics is off, it's just a blurry mess. When you turn it on, look at all those things just shook, and you can see how many stars are here, right? So many. This is the galactic center, and this is what they're actually looking at in that image that I showed here when I turn this off. This laser image down here. This is them pointing at the galactic center to do those observations you just saw. But that is the way that that you can overcome some of the atmospheric seeing from the ground. But it's expensive. You have to have a special system and this whole thing with the vibrating mirror. But that's how you overcome that. So, Vitalis asked a question. Does Hubble operate automatically, or do we tell it to look like it from Earth? Well, let me talk about how telescopes just operate on the whole. So, with any telescope, with all of these telescopes, there are groups that get together and operate the telescopes together or individually telescopes. So like, you know, the Keck telescopes has an entire group that just operate only these two telescopes, right? But like some of the telescopes like the LBT here, and then there's a couple other ones, the Magellan and stuff. These telescopes are operated by a consortium of colleges that work together. And Hubble is operated by NASA and the Space Telescope Science Institute, but they also operate a couple other NASA telescopes. And once a year, or maybe twice a year, these consortiums, these groups, will put out a call for proposals to either people who are privileged to use the telescopes or to the public, anyone who can use the telescope. And what that call is, so like Hubble has a call for proposals, you can write a proposal saying, here's what I want to look at, and here's why I want to look at it, what exactly I'm going to look at it with, what instrument, how long, like what I expect to do with the data when it's done, and like how I can write papers and references to why that matters. And then a group will get together, convened by the same organization of scientists, who will read all the proposals and rank them, essentially. They split them up into subgroups based on science and rank them, and then divvy up an amount of time on those telescopes to the people who got the best ranked, and the ranking could be based on scientific impact or novel science, or like things that like it mostly it's ranked essentially like what is the thing we think will work and will provide more scientific impetus, will help provide graduate education, like research for grad students, like there's a bunch of stuff, and it's like a pretty cool process. It's just very competitive for some telescopes, and so then once the telescope proposals are all accepted, then the people who run it schedule all the data for the whole year. They say, okay, well, here's our whole year or our whole semester, what we're going to observe on what night, who's going to get what night of telescope observing. So like when I would propose for the 2.4 meter telescope, we would get like 5 nights because it wasn't a very popular telescope to use, and we had a lot of time on it. So we get like 5 nights, and it'd be like in May 14 through 19, 14, 15, 16, 17, 18, 14 through 18, excuse me. You have those 5 nights. So I have to fly out from where I lived and then go up to the mountain and then run the telescope from a little control room those 5 nights. And if it's clouded out, sorry, tough. If you don't get the data you want, that's it. You got the nights. You got to hope that the weather's fine. Hubble, being in space, doesn't have to worry about weather. And when it gets scheduled, it's not a thing where you fly out to the telescope, as you probably would expect, Metellus. Instead, what happens is you get your time, and then they put it into a scheduler, and at the time, the telescope, people at a control room at Space Telescope will program in, this is the time and when we're going to observe and how long and everything, based on what you've written up. You've written up all the stuff. You're like, here's where I want it to point and for how long and how I'm going to get to point to this. Because you can't just say like, point to this spot in the sky. You kind of say, point to this spot in the sky, but that's kind of a rough thing, right? So like if I point here, like there's a rough, I'm going to point towards my webcam, but then I have to use some fine guidance to move it so I'm just directly pointing at my webcam, right? Beep, boop, 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 beep. Like, and so you'd say, I want to point Hubble at one spot, but then I have to do some fine motor so that Hubble actually looks at me. And so Hubble, and you do this with any telescope, but Hubble, you have to do it automatically. You have to do it. And there's people who will do a little bit, but it takes some time, who do a little bit of back and forth. But then they'll program it, and it'll automatically slew to the place it wants, and then start taking the data that you want. Once it's guided and you have the evidence that it's actually looking at the object you care about. Which has worked for the 30 years it's been up there. Hubble telescope is older than the film Jurassic Park, 1990, and it's a pretty good system, right? So here's the big problem about putting things. Here's a couple problems about putting telescopes on the ground. One, pretty much everywhere has a lot of light pollution, and so what you want is you want a place that doesn't have a lot of light pollution, which is why Chile down here is often used, and why you want to put something maybe on the Big Island of Hawaii, which is down here. There are quite a few telescopes. There's a lot of telescopes we don't know about that are pointing towards the Earth, like spy satellite telescopes. We don't know about those. But in terms of space telescope, there's maybe 10 to 20 or more, if you count ones that have left and are going out towards, Voyagers and stuff. But like orbiting the planet or in those, 10 to 20-ish. I think. I wonder if there's a website. This is like list of current space telescopes. List of space telescopes. The problem is these, I don't know if they're still existing. Gosh, there must be a lot more. Yeah, it must be more. It must be more like 50 to 60, maybe even 100. There's a lot. Luckily, there's... So Hubble is the best. I'll talk about that in just a second when I get to James Webb, in a little bit. The thing is you want to put telescopes on the planet in places where it's dark and also places where there's not a lot of high on mountains, so you're limited, and you want to kind of keep it near the equator, because if you're up here, then it moves. You're not going to get as much of the sky as if you are near the equator, where you can get the north and southern hemispheres. So this band here has a lot of islands where telescopes have been proposed, like the Canary Islands and Hawaii, where telescopes have been built or put. But also, there's a set of famous telescopes in Los Angeles. There's a set of famous telescopes in Chile, where the southern hemisphere gets a lot of its telescopes. Australia has a lot of great telescopes, Southern African large telescopes there in Southern Africa. So Hubble, why is it the best if there's other ones? Well, it turns out that while there are newer telescopes, those telescopes operate at a different wavelength than Hubble. And so Hubble is the best mostly because when we say best, that it really doesn't have any meaning. But Hubble is still thought of as being very important because it operates at wavelengths we can see with our eyes. And while it was built in 1990 and launched in 1990, built earlier in 1990, but launched in 1990, we've gone back multiple times to fix it and also replace whole instruments. And when you put a new instrument in there, that changes the capabilities of it, which allows it to take those spectacular images. And because it operates at visible wavelengths, the images are ones that we just like. No one looks at X-ray images because they're not as, the resolution. And so in terms of imaging in the ultraviolet and optical, it's the only telescope that does this, and it's the largest mirror in space that does this. It will be succeeded by the James Webb Space Telescope, but it won't operate at the same wavelengths. It'll operate at slightly longer wavelengths, but it will have a better resolution because there's a bigger mirror, which I'll talk about in a second. We talked about this last time, which is that you have to put certain telescopes in space or else the light doesn't get through the atmosphere. Like you have to put all the X-rays and ultraviolet ones in space. You have to put in infrared telescopes generally in space. Radio's here good on the ground, but longer wavelength radio, our atmosphere just blocks it. And so you'd want to put a telescope like Keck. The Keck telescopes are on the top of Mauna Kea because this whole thing is a little less, it's less opaque because you're up above so much atmosphere being on the top of that volcano there. So let me just show you some telescopes from across the wavelength regime. This is a gamma ray telescope called the Compton Gamma Ray Observatory. So it operates at incredibly high energies over here, which is why it's got no mirrors. It just has gamma ray detectors in there that are looking for gamma rays across the sky, essentially to, once you look at a gamma ray and you see these high energy sources from space, then you can tell other telescopes, hey, point to that area and see if there's something else that you can see in the sky that's at that area where we just caught these gamma rays. And Chandra I talked about last time, which is an X-ray telescope, and this is an optical infrared image with X-rays, like overlaid with these little dots, because Chandra doesn't have the greatest resolution. It's pretty good resolution, but it can mostly just see X-rays where other telescopes cannot, and it's mostly just very long because you have to barely touch the X-rays to kind of get them to focus. You can't just use a mirror and bounce them off the mirror. They'll go right through the mirror. But if you have a grazing angle, they'll bounce off. Similar to like if you want to focus a stream of bulls, you can't just like put a wall, like a bull and have them get caught. You have to like narrow down their pathway and they'll slowly over a long period of time, which is why it's so long. In the ultraviolet, we had a telescope that doesn't isn't being used anymore, called the Galaxy Evolution Explorer, or GALEX, which is ultraviolet. It was a smaller mirror, but it was still one of the only telescopes that may have only focused on ultraviolet, something you can't do from the ground. And Hubble has ultraviolet capabilities, but it currently is the only telescope that has ultraviolet capabilities. And well, why would you care about gamma rays or X-rays or ultraviolet? Well, different processes in space give off light. So if you want to study stars being born in the nearby universe, if you want to look at a galaxy and see, like, I want to look for where the stars are being born, then UV telescopes are pretty great, and Hubble can also see that. The problem is that when Hubble goes offline at some point in the next 5-10 years, there will be no replacement in the ultraviolet, and that's something that scientists are worried about. In the infrared, there was a telescope called Spitzer, and Spitzer was a telescope that was, one of the instruments was here at the University of Arizona by my boss and her husband. They worked on one of the instruments here, and now they work on another instrument on a telescope we'll talk about in a second. But Spitzer was smaller than Hubble, but was one of the only telescopes that at the time looked at this entire chunk of the wavelength regime of light, right? Like, essentially, if you look on this, it looked, all of this windows out here could only be done by Spitzer, right? And that's why they have a little picture of Spitzer here. What's cute, Spitzer, if you go to the National Air and Space Museum, there's Hubble, but they have like a full-size Hubble model, but they have like a little model of Spitzer there as well. And I'm hoping the telescope I work on also gets to, is popular enough and works and successful that it can be in the National Air and Space Museum, because it'd be cool to work on something that's in, a Smithsonian. The infrared telescope, another infrared telescope that I care about a lot is called WISE, the Wide Field Infrared Survey Explorer. It's probably much of my career is based on this telescope, which imaged the whole sky, all of the sky, every patch of the sky imaged in the infrared at a set of wavelengths that are really vital for the type of work that I do. And so, like, using this data is been really instrumental for understanding supermassive black holes, which is pretty cool. In the microwave and sub-millimeter, which is between infrared and microwave, there's a telescope called the Herschel Space Observatory that existed. And Herschel, again, small mirror, but looked at long enough wavelengths. And then the radio, and I talked about radio last time with the Arecibo, but there's also other ways of getting radio as well. And you need a very large mirror. The other telescope I want to talk about is this one. This is the James Webb Space Telescope. And for that, let's look at a different image. Here's James Webb, kind of a fancy glossy image. James Webb will be launched next year. I work on the main camera on it, which is called NearCam. And it is designed to look at a wavelength that Hubble could just barely get into in the infrared at a resolution that Hubble could not match, with a mirror that is much larger than Hubble's, right? So you can see here pictures. These are Hubble and some famous Hubble images. So you can see the resolution that Hubble can get, but also you can see that there's a lot of dust that's blocking your way. This is a baby star forming region, and this dust you can't see through the dust to see any stars there. This is another this is the Pillars of Creation. We can actually hear, it's pretty cute. You can turn off this right now. We can go to the Pillars of Creation now. You ready for this charming thing? So let's fly to the Pillars of Creation. Here's the Pillars of Creation. Kind of looks like a foot. In Space Engine. So I can, put them over here above my head, and then turn on the internet again, and you can not the internet, the PowerPoint, and you can see how they've simulated the Pillars of Creation in Space Engine, and then how it actually looks with Hubble, right? Maybe I'm being unfair. I can crank up our ability, our exposure. There you go. Now it's a little more fair, right? But you can see that the Hubble image is incredible. It's one of the most beautiful things we've ever seen, and it's another baby star forming region where you're seeing these like groups where stars are being born inside of these gas and dust clouds. And the dust, though, and the gas blocks their way to see because optical light just hits that dust and hits that gas, just is like absorbed and is like, sorry, I can't get through. With the infrared, you can actually see through that. And so having a telescope that can see through that, pretty important, pretty cool. If we go back to the keynote here, this. You can see this is an image of a galaxy. Is this the Whirlpool Galaxy? It's the Whirlpool Galaxy. Here, we'll show you this. It's kind of fun. Got to fly outside of our Milky Way. Shoop. So here's the Whirlpool. And we go back to here. Maybe it isn't Whirlpool. Maybe it's something else. Maybe it's not Whirlpool Galaxy. It doesn't matter. And then you've got the Eagle Nebula. Like, these are cool pictures, but we want a bigger mirror. I can operate at different wavelengths, and that's where James Webb Space Telescope comes in. So you can see the mirror sizes compared with a person here, right? So Metalis has asked, if astronomers are concerned about not having the wavelength that the Hubble spoke to detect, won't they build a new one with that capability too? Well, it's true. Yes. So new telescopes will hopefully be built. This one right here, it was proposed 20 years ago, right after Hubble launched 30 years ago. And so it's been, and it's going to focus mostly on the infrared because it's very expensive to add in other capabilities, and they built it specifically for the infrared. If we build another telescope that has UV and optical, there's one called LUVOIR that's been proposed, and LUVOIR should ideally cover both ultraviolet and the optical and the infrared, which is why it's UVOIR, but it's expensive. James Webb Space Telescope here is like $10+ billion, right? That's an expensive telescope. And if we have another $50 billion lying around and the ability to put that, like, people might want to say, well, we should use that money on outreach and other things in NASA. But James Webb has been a big budget hog. Exactly. It takes a lot of time and resources. Here's the parts of it. It's got light that comes in here, bounces off the primary mirror, off the secondary mirror, in through this little thing here to where the telescope instruments are, and the ISIN, the Integrated Science Instrument Module. So NIRCam, the instrument I work on, is sitting in the back here. It also sits on this sun shield, which acts like a parasol to keep it cold, and I'll talk about that a little bit later. Down here is the spacecraft bus, which is all the parts that keep it actually, moving and rotating to where it needs to go in space. There's a little thing on the back here which helps offset angular momentum. And then there's, down at the bottom, there should be a solar panel. Here are the 4 instruments that are actually inside and, plugged in right now. There's NIRCam, the telescope instrument I work on. There's NIRSPEC down here. There's MIRI, which is the mid-infrared instrument. NIRSPEC is a spectrograph, which means it acts like a very fancy prism, where the light that comes in is spread by wavelength. And you can see the components of the light. And then here is NIRIS, which is a slitless spectrograph, which is a very specific capability that I don't want to really get into at the moment. But NIRCam is 2 cameras sandwiched on each other, which looks like it's reflected across this thing right here. You can see this part up here is the same as this, and this part up here is the same as this. This box is the same as this. It's actually 2 cameras that look over a rectangular region of the sky. And inside of those 2 cameras, it's exactly the same, and it can take 2 images, one of short wavelength light and one of long wavelength light at the same time, which is very cool. Here's the camera zoomed in, NIRCam, where you can see the light will come into this on either side and go into the instrument. These big things that look like film canisters are the filter wheels. So the filters in there will rotate around, so the light will pass through the filters there. So if you want to put a specific filter and get only what wavelength you care about, that's how you do that. So you asked a question, Metalis, about what's the farthest we can see earlier. How far can we see into space? And this is it. This is the farthest we can see into space. This is the Hubble Ultra Deep Field, one of the most famous. It's actually technically there's farther that we can see, but for right now, this is what I want to get into. There's ways in which you can use gravitational lensing to see farther, but this kind of represents the same sort of thing. This image here, very famous. Why am I? Oh, that's the edge of the screen. What am I talking about? I'm confused, but this image all around us here, all around me here, is an image where James Webb looked at. I wonder if is HGDF. I doubt it. it's not. Nope. All right. Where Hubble essentially looked at one region of the sky where there wasn't a lot of bright stars, just so that the stars wouldn't get in the way for like a long period of time. Just open the shutter and kept coming back and adding it and trying to get as faint a galaxy as it can. And that's what you're seeing here. Every part of the sky is as populated with galaxies as this right here. Every part is like this, where there are stars that, like, or there are galaxies beyond galaxies, beyond galaxies, beyond galaxies. And essentially, this is a picture showing the history of galaxies over time, where the galaxies that are closer by generally are larger, although there's some galaxies that just are inherently smaller. And the galaxies that are really small and fuzzy and generally red are either galaxies that are inherently small and fuzzy or really, really far away ones. It's tough to tell if something's really small or really far away when you're in astronomy. And so this right here is one of the great images in all of astronomy, the Hubble Ultra Deep Field. And James Webb will look at this exact same region over something that's much, 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 much larger. The survey that I work on is called JWST, and it'll make this picture look like I guess I can do this. Like, it'll be like this, and we'll still have, much, much larger. Like, this is one of the famous ones, and it'll just be a tiny chunk of all of JWST, because James Webb has a larger mirror and a larger instrument field that can search. It's pretty cool. So how far? Well, the farthest galaxies we can see, so if I bring up the farthest galaxy, it's called GNZ 11, I think. Oh, is there an even farther one? List of the most distant astronomical objects. So here we go. Yeah, GNZ 11. So I'm going to bring up my internet right now. So here is a similar thing, the Hubble Ultra Deep. This is a good image, and there's a little blob here, and you can see the blob here, and this blob here is probably the farthest, and it's GNZ 11, and it says it's 13.4 billion years distant, right? 13.4 billion years distant. So the universe is only 13.6 billion years, so you can't see farther than that. And so essentially you're seeing almost, the farthest you can possibly see. 400 million years after the Big Bang. Big Bang's universe is only 400 million years old, and you see it in this galaxy gave the light off that moved into space. This galaxy, we call it a redshift 11. We're going to find 10s, 20s of these with our survey JWST, and even farther. We're going to find a lot of galaxies like this. It'll make GNZ 11 look like, oh yeah, you're kind of fun. So the universe is expanding, but it's complicated in terms of how you actually measure distance, but generally I measure distance in terms of the distance that, it's the way that you want to think about this. Ned Wright Cosmological calculator. So this is our website to go to here. Can you see the Ned Wright Cosmology calculator? Yeah. So if we put in 11 and click flat for a flat universe, it'll give a bunch of stuff here, right? In terms of light travel time, and the co-moving radial distance is 98.601.1, or 32 gigalight years, 32 billion light years, which is kind of like what you're saying, right? And that's different than the angular size distance and the luminosity distance, 385 billion light years, right? What you want, mostly what I look at, is the light travel time. How long did it take the light to travel? Because it turns out that distances make a lot of sense because the universe is expanding, which is stretching out distances. So what really is a meter when the universe is stretching? So I generally look at the light travel time. How long did the light travel? Because distance is relative, man. But light, and it depends. And you can go and click on what is co-moving radial distance and read about this crazy, the universe is expanding and you have these cones and stuff. I don't want to get into cosmology right now. But you can use the Ned Wright Cosmology calculator to put a redshift in here and tell you what the light travel time was, which is nice. Because that's kind of the thing where, that at least makes sense in terms of, what am I doing? This. That at least makes sense in terms of how long has light been traveling, because light, we know, travels at the speed of light. Okay? Yeah. Distance, its distance is, it's nonsensical, because, it's not like the universe is static. It's when the light left, the galaxy is still moving away, And like, so is it where it is now? Who cares where it is now? What, like, mostly just think of how long is it taken for the light to get to us, because that at least, you know, tells you what I care about, which is when I look at a galaxy and I see it that the light has traveled for 11.549 billion years, or something like that, or 13 billion years. I can tell you how old was the universe when that light was set, and when I can tell you that matters because of the evolution of galaxies, because of the evolution of the universe. We can, like, it's like saying, like, I have a picture of something that's the 1860s. I don't care how far away that person is in the past, in the 1860s or whatever. I care about, this is an 1860s person, this is an 1870s. This is a galaxy at this distance, or at this, not distance, at this age. This is a galaxy at this age of the universe. This is a galaxy at this age of the universe, because you can look at how galaxies change as a function of the age of the universe. Like a bird said, how will these newly discovered regions get their names? Well, generally, so that galaxy is called GNZ 11 because it's a Goods North Redshift 11 galaxy. Goods is the Great Observatory. Goods. What is Goods? The Great Observatory Origins Deep Survey. So it's just a survey that they named Great Observatory. So generally what they'll probably be is, because the survey that I'm working on will be called JADES, we'll probably call them JADE Z11, JADE Z13, JADE Z14, or something like that, which is not that exciting. I'd like to name them after my boss, Dr. Marshall Ricci. I'd like to call them Ricci 1 or Ricci 2, Ricci 3, but I haven't told anybody about that yet. And my job, what I work on with JADES, is I'm working on how we can take images like this and turn it into actual distances to galaxies, which is a very complicated thing that I can give a talk on in the future. So Metalis is asking, if we can see that far, and looking into space is looking into the past, shouldn't we be able to see light from this Big Bang at the furthest distance? So we can the farthest we can see is not the Big Bang, we can see what's left over from the Big Bang. And I'm going to talk about cosmology, I think, next time, because I know that this is segueing into it. But like, we'll come to that, but we can't actually see the Big Bang because the universe was opaque for a long period of time, a little bit of time before 400,000 years after the Big Bang. We can see that opaqueness, and I'll talk about that in a couple weeks, so I'll have to come back. But I just want to finish up with a little bit here. The other thing that James Webb will do is it will look at galaxies like that are nearby with unprecedented detail. The galaxies that are over here, these are some of, the farthest that we can see, like some far galaxies we can see like that have knots of star formation, and we're going to see them full. See galaxies that for Hubble would look like this, more like this, or more like this, which is great. As I showed earlier, for regions of light where you can barely see because there's a bunch of dust and gas, James Webb will see through them. This is the same region where you're actually seeing the stars inside of this cocoon. Very cool. Similarly, like you see, this is like a region of gas and dust that is from star formation blown off from a star. This blue star is blowing gas and dust out. We'll be able to see that. We'll be able to look at atmospheres of planets like exoplanets. And I talked about this a couple months ago. We'll be able to take actual images of planets. Like this will be this is like a simulation, but you have a star and then you have a little planet around it, and we can actually use multiple filters to take actual images of stars by blocking the planets by blocking the light of the stars, which is pretty cool. And then finally, it's going to be launched. It's not like the Hubble. Hubble was launched inside of the space shuttle. They put it in the space shuttle. They launched the space shuttle. Went out to space. It deployed it. You have to put James Webb, which is the size of a tennis court, inside of a rocket that's much less than the size of a tennis court. So to do that, this is how Hubble was launched. If you have never seen this image, they used the Canadarm to lift it up into space. This right here is called coronography, because this is a coronagraph right here. And you see the coronagraphs that are on NearCam right down here. Spot coronagraphs and there's little strip coronagraphs. So you have to fold it up. So here's an image of James Webb all folded up. JWST, coronography. Coronavirus. Yes, a coronograph. You can see that it has to fold the sides in, and then it folds the mirror the secondary mirror all up, and the sunshade is actually right here all folded up. And when it goes out into space, it will take about a month to go from the Earth and go all the way out. It's not orbiting the Earth like Hubble is. Hubble just orbits our planet, which is why you get those beautiful shots of Hubble orbiting the planet. Like, if I go all the way back to the start here, you get an image like this because Hubble's orbiting the planet. You can actually go out and fix it, like in the film Gravity, because Hubble's orbiting the planet. James Webb goes 1 million miles away, where it points away from the sun and the Earth to look at space, right? And you can see here, this is why it has this sunshade here, because it keeps it on the hot side pointing towards the sun and the earth. It's 180 degrees, 5 degrees Fahrenheit all the time. Not good. On the cold side, negative 388 degrees Fahrenheit. Great, because when you have an infrared telescope, you really want to keep it cold so that the instrument itself isn't glowing in the light. Because if you took a picture of me in infrared light right now, I would be glowing, right? I wish I could show you. I have my Nintendo Switch here. This on the right Joy-Con on the bottom, this right here is an infrared camera. And you can use infrared cameras. Like if I could show you the output of this infrared camera, you'd see that I was glowing in certain infrared wavelengths. And that's how they use it to detect like motion for when in Ring Fit you can put your finger here and on the Joy-Con and it'll detect your heart rate and it's pretty cool. Like how you can do that. The Labo also allows you to do that. And infrared cameras detect things that are warm. But that's bad if you are wanting an infrared camera to take pictures of space. If the camera itself is warm, then it would overwhelm the light from space and you wouldn't get any detection. This looks like it's orbiting things. It's actually orbiting a spot called L2. And so, gosh, does L2 exist? I doubt it. No. L2 is a spot. If I cancel, if I go back to, let me turn off my PowerPoint really quickly. Let's zoom out. Let's turn on this like that. Unless HDR is on. All right, good. Let's turn on the orbits. Bink. Whoa. So here is the Sun, Mercury, Venus, Earth, right? So Earth's up here. Let's rotate around. There we go. So this right here, gravitationally, there's a spot between the two of them where they're pulled by Sun and by the Earth in an amount that, compared with how it's going around, keeps it in the same spot. That's called Lagrange point 1. And there's a spot on the other side where it's moving really fast around here, and that needs to be pulled by a combination of the Earth and the Sun together, and that's called Lagrange point 2, and that's somewhere over here. And that Lagrange point 2, 1 million miles from the Earth, that's where it's orbiting. So it's well beyond the orbit of the moon. It's 1 million miles from the Earth, and it'll orbit this spot, just going in orbit around a stable point in the orbit in our solar system. Pretty cool. So it's not orbiting an object. There's actually objects out there already that are orbiting Lagrange point 2. It's been done before. You can see that they've built the sunshade so that if part of it gets ripped by a meteorite or something, it doesn't just all rip. It has like all these little folds in it that will allow it to release some tension and stuff. But that's what I want to talk about because it's now 6:03. We do. I mean, don't you radiate heat? Aren't you warm? Like your skin is warm. Like if I bring up like infrared picture of person. Turn on my internet again. Bink. Look at what a person looks like in the infrared. Right? This person right here in the infrared, you see that, their nose is kind of cold, but their mouth is really warm and the eyes are really warm. Their forehead's a little warm. Their hair is pretty cold, right? Their neck is warm. And so we all glow. We all are like a little flashlight of light, right? Here's a family. Infrared images of people. Ugh, gross. Right? Like, you are glowing. You just don't realize it. You are an infrared light flashlight. So yeah, sure. Superpowers. That's it. Yeah. Anyway, it's 6 o'clock. This was fun. Next time I'm going to start and do a little bit about cosmology, which is not my super strength, but I think there'll be some fun stuff there. But it was really fun. I'm sorry that the internet kind of died on me halfway through this. But I hope that you come back, and I really appreciate you all coming out and watching. If you're watching at home and you have questions, leave them in the comments. Do the like and subscribe thing. I don't know if that matters at all. I think many of you are probably already subscribed, but have a really great rest of your afternoon, evening, weekend, Labor Day weekend. Go out and look at the stars if you can. Watch my other series and learn, go out and look at the stars. It was wonderful to talk with you all. Bye, Metalis. Bye, Legged Bird. Bye, KJ, if you're still watching. Bye, anyone who's watching. Bye. Let's see. Now I have to do that thing where I